Hello friends. So today we are going to solve the questions from the modern physics, and all these questions are from the year 2014, and we are having a total of 7 questions. So first question, it states that hydrogen, deuterium, single ionized helium and double ionized lithium all have one electron around the nucleus. Consider an electron transition from n is equal to 2 to n is equal to 1 if the wavelengths of emitted radiations are lambda 1, lambda 2, lambda 3 and lambda 4 respectively for 4 elements, then approximately which one of the following is correct? So we have to find out the relationship between the wavelengths when the transition is from n is equal to 2 to n is equal to 1, and in hydrogen, deuterium, single ionized helium as well as double ionized lithium. Okay. So in this case, in all these elements which are given to us, one thing is common, that all of them are having one electron, so we can treat them as a hydrogen-like atom. So you can say all have one electron, therefore they can be treated like a hydrogen atom, and the transition is from N2 to N1, and based on this we are going to use the Rydberg formula for the wavelength. So transition is from N is equal to 2 to N is equal to 1. Therefore we can say the wavelength can be written as 1 upon lambda is equal to Rz square, and we start upon 1 upon 1 square minus 1 upon 2 square, and this comes as 3 by 4 Rz square. And here we can clearly see that this term 3 by 4 multiplied by R is a constant term. Therefore, we can write the equation that our lambda is proportional to 1 upon z square. And based on this value of z, we are going to find out how the lambda is going to behave. Okay. So the first element that is given to us is a hydrogen, and hydrogen means value of z is equal to 1, and the corresponding wavelength is given as lambda 1. So lambda 1 will be equal to, is proportional to 1 upon 1 square, giving us lambda 1 is proportional to 1. second element is our deuterium. Which gives us that the value of Z will be equal to 1. Therefore, here also value of lambda 2 is proportional to 1. Next is our helium 1 positive. And here in this case the value of Z will be equal to 2. Therefore, we get our lambda 3 is proportional to 1 upon 4. And finally, we are having lithium 2 positive. For this, value of Z will be equal to 3, giving us lambda 4 is proportional to 1 upon 9. Therefore, we can write the relationship between lambda 1, lambda 2, lambda 3 and lambda 4, and this relationship can be written as lambda 1 is equal to lambda 2 is equal to 4 times lambda 3 and is equal to 9 times lambda 4. So therefore, you can say option C is correct. Next question. It states that a metal surface is illuminated by light of two different wavelengths, 248 nanometer and 310 nanometer. The maximum speed of the photoelectrons corresponding to these wavelengths are U1 and U2 respectively. If the ratio of U1 to U2 is 2:1 and Hc is equal to 1240, the work function of the metal is nearly. So we are given two wavelengths. Let us assume that first wavelength is our lambda 1, which is our 248 nanometer, and the corresponding speed is our U1. Second wavelength is our lambda 2, which is given as 310 nanometer, and suppose the speed is given as U2. And relationship between U1 is equal to it is a ratio. So we are given as U1 is to U2 is equal to 2:1. Therefore, we can use the photoelectric equation which is our half m u square is equal to Hc upon lambda minus phi, that is our work function. So we can divide this equation into two parts. For lambda 1, we can write this as half m u1 square is equal to Hc upon lambda 1 minus phi, and second equation we can write as half m u2 square is equal to Hc upon lambda 2 minus phi. And we are given that our U1 is to U2 is 2:1. Given that U1 is to U2 is equal to 2:1, and therefore we can write that our U1 square is equal to 4 times U2 square, and this can be further modified as half m u1 square is equal to 4 times half m u2 square. So we already know our half m u1 and half m u2 square we already know. So we substitute them. We get this as Hc upon lambda 1 minus phi is equal to 4 times Hc upon lambda 2 minus of phi. And we just open the bracket. We can write this as 4 times Hc upon lambda 2 minus 4 times phi. And we can just make the adjustment in the equation, and we get this as 4 Hc upon lambda 2 minus Hc upon lambda 1 will be equal to 4 phi minus phi, giving us 3 phi. And from here we can write that our function, work function phi, we can take Hc as common. So this comes as Hc upon 3, and we have this as 4 times lambda 2 minus 1 upon lambda 1. All the values are given to us. So we can write that this is our 1240 divided by 3 and 4 divided by 310 minus 1 divided by 248. Therefore, the work function phi is approximately equal to 3.67 electron volt. So option number A is correct. A is correct. Next question. It states that the radiation corresponds to transition from 3 to 2 transition of a hydrogen atom falls on the metal to produce photoelectron. These electrons are made to enter a magnetic field of 3 into 10 to the power minus 4 Tesla if the radius of largest circular path followed by these electrons is 10 millimeter. The work function of the metal is close to. So in this case, the electron which will be produced as soon as it enter the magnetic field, it is bound to follow the circular path. Okay, so you have to keep this in mind. So first of all, we are going to find out the energy of the photon that is emitted when the transition takes between from 3 to 2. So we can say our energy of photon in 3 to 2 transition. And for nth level, we know the formula. We can say that energy level in hydrogen atom, we can write that E of n is equal to minus 13.6 upon n square electron volt. So therefore, we can say energy of the photon when the transition is going to take place from 3 to 2, and therefore we can write, let us suppose that energy of photon is represented as delta E. Therefore, we can write our delta E will be equal to our E3 minus E2. So we already know of E of n. So according to the levels 3 and 2, we can write our minus 13.3 will be our common term. This comes as our 3 square minus 1.2 square. And this comes as approximately as 1.89 electron volt. And as soon as the electron leaves the photoelectrons are emitted rather, and they enter the magnetic field, they are going to follow a circular path. Let us say that the radius of that circular path is represented as r. Therefore, we can write in the magnetic field we have our radius r will be equal to mv upon q multiplied by b. So here we can write our velocity v will be equal to qbr upon m. So based on this, we can find out the kinetic energy. Therefore, we can say kinetic energy will be equal to half m v square. We substitute value of v, we get this as our half m, and this will be our qb r whole square upon m square. Square cancel with m, and this comes as our half, and we are left with our qbr and whole square. We already know all these values, so substitute them, we are going to find out the kinetic energy. So we get kinetic energy is equal to half q is the charge on the electron, so divided by m. So this comes as 1.6 into 10 to the power minus 19 multiplied magnetic field 3 into 10 to the power minus 4, and radius is our 10 millimeter whole square divided by mass, that is our 9.1 into 10 to the power minus 31. So we get this energy will be approximately equal to 0.79 electron volt. Now we can use the photoelectric equation. You can say photoelectric equation, energy of the photon will be equal to 5 plus kinetic energy. Here energy is represented as delta E, so we substitute it, and therefore we can write that our work function phi will be equal to delta E minus kinetic energy, and delta E is our 1.89 and this is 0.79. This gives us that work function is equal to 1.1 electron volt. So option B is correct. Next question. It states that lambda, if the lambda cu is the wavelength of a k alpha X-ray line of a copper atomic number 29, and lambda mo is the wavelength of k alpha X-ray line of a molybdenum atomic number 42, then the ratio of lambda cu and lambda mo is close to. So here we are going to use the Moseley's law, and you can say that Moseley's law, and this gives us that our lambda is proportional to z minus 1 whole square. So we can reformulate this Moseley law equation according to the two elements, or we can say two wavelength, and directly write their ratio. So we get this as lambda Cu divided by lambda Mo will be equal to z Cu minus 1 whole square and z Mo minus 1 whole square, and their values are given to us. We have 42 minus 1 and we have 29 minus 1, and this is approximately equal to 2.14. So the option B is correct. Next question. It states that the forward bias diode connection is, so in these all four options we have to check rather that which of the diode is forward bias or not. So for forward bias we have to remember that our diode consisting of one we call it P, other one is we call it N, and in normal circumstances we say that our P should be connected to a positive and N should be connected to a negative. But this can be interpreted in other way also, that the P should be connected to a higher and N should be connected to a lower. This also results in a forward bias. Therefore, you can say that our option A, our P is connected to higher and N is connected to the lower, so this results in forward bias. In case of option B, P is connected to minus and N is also connected to minus, so this is at the same potential, it is wrong. In option C, P is connected to plus 2 and N is connected to plus 4, so this is also wrong. And finally, we have our option D, P is connected to a lower one and N is connected to higher potential, so this is also wrong. So option A is correct. Option A is correct. Okay. So the forward bias and reverse bias is ideally basically for the with respectively the higher as well as the lower potential. Next question. It states that during the propagation of electromagnetic wave in a medium, we have to find out what will be the relationship between electrical energy density as well as magnetic density in all the four options, whether they are equal, half, or double, or the value is 0. Okay. So in this case we have to remember, this is general information, that our for a EM wave, the electric field is perpendicular to the magnetic field and they are also perpendicular to the direction of the propagation, and perpendicular to the direction of propagation. And the value of electric energy density, or formula rather. Electric energy density represented as UE will be equal to half epsilon E square. Similarly, we can write magnetic energy density that is our U of B will be equal to half B square upon mu. And although with respect to formula it looks like they will be different, but the normal relationship between these two is that they has to be equal. Therefore, we can say option C is correct. Next question. It states that the magnetic field in a traveling electromagnetic wave has a peak value of 20 nanotesla. The peak value of electric field strength is. So this is directly based on the formula. The relationship between electric field and magnetic field, or we can say ratio of electric field and magnetic field, is equal to C. So we can say electric field ratio magnetic field is equal to C. So from here we can write electric field is equal to C times magnetic field, where C is the speed of light. We substitute the values. E will be equal to, electric field is our 3 into 10 to the power 8. Magnetic field is given as 20 nanotesla. So we can write 20 into 10 to the power minus 9. So this gives us electric field is equal to 6 volt per meter. So option B is correct. So this completes all the 7 questions from the year 2014. Thank you.